Hi, this is Sir Eldon, and this is Jama Physics 1. I hope you have your notebook, your pen, your calculators, and snacks with you. So for this video lecture series, we will be talking about momentum, impulse, and collisions. Our objectives for today are the following. Relate the momentum, impulse, force, and time of contact in a system. Solve problems involving impulse momentum theorem and the law of conservation of momentum. Apply impulse momentum theorem in explaining the necessary conditions for conservation of linear momentum to be valid. And lastly, to predict motion of constituent particles or different types of collisions, and that is elastic and inelastic collisions. So, let's start. This time we will be talking about momentum, impulse, and collisions. This video lecture series will help us understand what will happen after a bowling ball hits the bowling pin. Where will the car move if it collides with a big truck? For this module, we will be talking about momentum and relate it with forces and how understanding it will save lives. We have expressed Newton's second law of motion, that is all net forces is equal to m times acceleration. Also, second law of motion has been re-expressed in terms of work-energy theorem. We've seen that from our work and kinetic energy. Work-energy theorem have helped us tackle complex physics problems and led us to the law of conservation of energy. We will still be using Newton's second law of motion to understand momentum. Suppose a particle or an object with a constant mass m is moving. Since we know that A is just equal to dV over dt, we can express Newton's second law as net forces is just equal to m times dV over dt, or it is also equivalent to summation of forces is just equal to d times m over v over dt. We move the mass m inside the derivative because it is a constant and not changing it, and it could easily interchange. This expression now tells us that a net force acting on a particle is equal to the time rate of change of the combination mv. The product of the particle's mass and velocity. Take note, velocity. This combination is actually momentum or linear momentum of our particle. Using the notation p, small letter p, for momentum, we now have p that is now equal to mass times the velocity. This expression tells us that the greater the mass and speed v of a particle, the greater is its magnitude of momentum. Take note, I'm talking about magnitude. Momentum, as the notation shows, is a vector quantity, of which it will follow the direction of the particle's velocity. A truck rolling down a hill has a more momentum than a roller skate with the same speed. If the truck is at rest and the roller skate is moving, then the skates has more momentum than the truck. Since we can see that momentum is just a vector, then we could have the vector components. We could have momentum along the x-axis, or the y, and then the z-axis, which the velocities will follow also. The SI unit for our momentum is kilograms times meters per second. Take note, we could only use this equation P is equal to mv if our mass is in kilograms and our velocity is in meters per second. And please don't forget about the directions of your velocity. It could be moving to the right, to the left, up, or going down. Let's have example number 1. On a highway, a truck and an SUV were seen moving in the same direction. A truck has a mass of 10,000 kilograms and is moving at a speed of 12 meters per second. The SUV has a mass of 2,000 kilograms. A. Calculate the momentum of the truck. B. Calculate the speed of the SUV to attain the same magnitude of momentum as the truck. Example number 1 calls only for the magnitude of the momentum and velocity. Thus, we could neglect the directions. Also, the SUV and the truck are only moving along the horizontal axis. Solving for letter A is very easy. Since we are only after for the magnitude and the truck is only moving linearly, we can make use of this formula, P is equal to mv. And we note that the car is moving towards the positive x direction. Hence, we have the speed 12, or hence we have the velocity positive 12 meters per second. We now have the momentum of the truck, that is positive 1.200 times 10 raised to 5 kilogram meters per second. The magnitude of the truck's momentum is 1.200 times 10 raised to 5 kilogram meters per second. Solving for letter B is also easy. For the SUV to have the same magnitude of the momentum as the truck, it must attain a certain speed. The magnitude of the SUV's momentum should be equal to 1.200 times 10 raised to 5 kilogram meters per second. Hence, we could have this equation. PS is just equal to ms times Vs. Manipulating the equation to get the speed of the SUV, we could have Vs is equal to PS over ms. And we could get the speed that is 60.00 meters per second. The SUV must have a speed of 60 meters per second for the magnitude of its momentum to be the same of the truck. Going back to Newton's second law of motion, our definition now is the net force acting on a particle is equal to the time rate of change of momentum of the particle. This definition is how Newton originally stated his second law and called momentum a quantity of motion. This new definition or this old definition for us tells us that a rapid change in momentum requires a large net force, while a very gradual change in momentum requires less net force. This understanding helps scientists and engineers to design safety devices for cars such as airbags. Motion is not always the same. There are times that we need to apply a force to a moving object. Applying a net force for a given period changes the momentum of an object. The impulse of a constant net force, denoted by big letter J, is defined as the product of the net force and the time interval. Momentum and impulse are closely connected to each other. Impulse is a vector quantity. Its direction is the same as the net force. The magnitude is the product of a net force and the length of time that the net force acts. Impulse will have an SI unit of Newton second. Since 1 Newton is just equal to 1 kilogram times meters per second squared, an alternative SI unit for impulse is also kilogram meters per second, which is the same as the momentum. We can extend our understanding of the impulse to non-constant net forces. For this, we make use of our integral calculus. With this definition, the impulse momentum is still valid, when the net force varies with time. Now we can describe an average net force such that even when the net force is not constant, the impulse is defined as average force times the change in time. This general equation for impulse can be graphically understood using the area under the curve of a force versus time graph. Going back to the new definition of Newton's second law of motion. If the net force is constant, dp over dt is also constant. In that case, dp over dt is equal to the change in momentum p2 minus p1 during the time interval t2 minus t1. Doing the necessary algebra, we could have this final equation wherein we have impulse is just equal to p2 minus p1, or basically that is just impulse is just equal to the change in momentum. This is actually our impulse momentum theorem. This equation tells us that the change in momentum of a particle during a time interval equals the impulse of the net force that acts on the particle during the time interval. So we have this example. If the brakes of your car are malfunctioning and you have a choice to either crash your car between a wall and haystacks, it would be best to choose the haystacks. Either of the two choices, the car will always experience the same change in momentum, but the car will experience different impulse forces and different time intervals. Hence, it would be better to choose the haystack because it will only experience a small amount of force over a long period of time, comparing it with a wall wherein you will experience an impulse force that is greater compared to the haystack. We now have this example. Example number 2. In a crash test, a car of mass 1,500 kg collides with a wall. The initial and final velocities of the car are v1 is equal to negative 15 meters per second and v2 is equal to 2.600 meters per second respectively. If the collision lasts for 0.150 seconds, A. Solve for the initial and final momentum of the car. B. Solve for the impulse caused by the collision. And C. Calculate for the average force exerted on the car by the wall. We could now illustrate our problem. We could have this illustration where you have V1, a velocity of negative 15 meters per second, which is going to the left, and you have V2 that is going to the right at 2.600 meters per second. Take note that momentum will always use the velocities. That's why we need to make sure that we include the directions. Since we are already given the mass and the initial and final velocity, we can directly substitute these quantities to our formula for the momentum. We now have the initial momentum. The initial momentum is now equal to negative 2.250 times 10 raised to 4 kilogram meters per second, and the final momentum of positive 3.900 times 10 raised to 3 kilogram meters per second. Solving for letter B will be easier. From part A, we could easily solve for the impulse from the collision using the momentum impulse theorem. So, impulse is just equal to the change in momentum. That's why you have P2 minus P1. And now we have our impulse that is positive 2.640 times 10 raised to 4 kilogram meters per second. It is positive because most probably the force being acted on our car is pointing towards that direction, towards the positive x direction. Solving for letter C, using the time that the car and the wall are in contact and the impulse from part B, we can easily solve for the average force exerted by the wall using the definition of impulse, wherein impulse is just equal to the average force times the change in time, or delta t. Manipulating this equation, we could actually solve for the average force. The average force now is equal to positive 1.760 times 10 raised to 5 newtons. Positive because our impulse is also in the positive side. And then we now go to conservation of momentum. But before that, from the previous module or from the previous videos, we have encountered problems that are difficult to analyze using only Newton's laws of motion. That's why we have used different approaches. We've used conservation of energy. We now consider another situation in which we have a 60 kilogram archer standing on a frictionless ice and fires a 0.50 kilogram arrow horizontally at a speed of 50 meters per second. Analyzing using the third law of motion, we know that the force exerted by the bow on the arrow is matched by a force in the opposite direction on the bow, or on the archer. This force causes the archer to slide backward on the ice. But with what speed? We cannot use directly either Newton's second law of motion or conservation of energy because the information is insufficient. The concept of conservation of momentum is particularly very important for these kinds of situations. In this kind of situation, we have two or more bodies that are interacting. We now employ our strategies from the previous videos or from the previous lectures. That is, we consider first that this is an idealized system of two bodies that are interacting with each other and not with anything else. One good example for this is these two astronauts who touch each other as they freely float in the zero gravity environment. According to Newton's third law of motion, the forces that they exert with each other are always equal in magnitude. Again, according to Newton's third law of motion, the forces that they exert with each other are always equal in magnitude, but opposite in direction. For this, the impulses that act on each of the astronauts are equal and opposite. Also, the changes in momentum are also equal and opposite. In the figure, the net force Fb on A and Fa on B will have an equal magnitude but opposite direction. That's why we have Fb on A equal to negative Fa on B. Using the momentum definition of Newton's second law of motion, we know that the net force is just equal to the rates of change of momenta of these two astronauts. We have Fa on B equal to dPb over dt and Fb on A dPa over dt. The momentum of each astronaut changes, and these changes are related to each other by third law of motion. So from Fb on A equal to negative Fa on B, we can have Fb on A plus Fa on B equal to 0. Subsequently, we can have now dPa over dt plus dPb over dt, that is just equal now to the change of momentum of the system over dt, equal now to 0. Note that the change in Pa plus Pb over dt is equal to the rate of change of two momenta, and these rates of change are equal and opposite. For this, we have the rate of change of the momentum of astronaut A and the rate of change of momentum of astronaut B. So the rate of change of the vector sum PA plus PB is just equal to 0. We now have the definition of the total momentum of the system of two objects interacting with each other as the vector sum of the momenta of individual objects. That's why we have capital letter P is equal to small letter PA plus PB, or the total momentum is just equal to the momentum of each objects. And now we have dP over dt is just equal to 0. The time rate of change of the total momentum P is just equal to 0. Hence, P or total momentum is just equal to 0. The total momentum of the system is constant, even if the individual momenta of the particles that make up of the systems can change. This understanding will be only true if that the forces acting on our astronauts are purely internal forces, meaning the forces that the particles of the systems are being exerted on each other. Forces exerted on any part of the system by some other object outside are called the external forces. If there are no external forces, we call this system as an isolated system. So if we have the astronaut wherein no net forces acting on them, external forces acting on them, we only have the internal forces, then this is an example of an isolated system. There are instances that there are external forces. For this, they may be included on the left side of our equation, along with our internal forces. Then the total momentum in general is not constant. But if the vector sum of these external forces is equal to 0, then these forces will have no effect. Thus, dP over dt is still equal to 0. In general, the simplest form of the principle of the conservation of momentum is if the vector sum of the external forces on a system is 0, the total momentum of the system is constant, or equivalent, the total momentum initial should be equal to the total momentum final. This principle tells us that the total momentum of an isolated system is always equal to its initial momentum. We go back now to our example number 3, wherein we have a 60 kg archer standing on a frictionless ice and fires a 0.50 kg arrow horizontally at a speed of 50 meters per second. With what velocity does the archer move across the ice after firing the arrow? The problem is now easy to analyze and to solve now that we have understood conservation of momentum. Note that this system is not an isolated system, and there are external forces acting. There are gravitational forces and normal forces from the ice, but understand also that these forces are independent from our motion. The forces are acting on the vertical axis while our motion is horizontal. Thus, there are no external forces acting on the horizontal axis, and we can consider this as an isolated system in terms of horizontal components of the momentum. We let the direction traveled by the arrow as our positive x direction. Since this is an isolated system, we can use conservation of momentum, wherein we have the initial momentum equal the final momentum. We will use subscript A for the arrow and B for the archer. And we know that our archer and arrow are initially at rest, so their initial velocities are 0. Hence, our initial momentum is just equal to 0. So if we have the illustration, we could have this one. And for our solution, getting for the speed, since our initial momentum is 0, we only have the final momentum. And doing the necessary algebra, we could get actually the final velocity of the archer. So after firing the arrow, the archer will have a velocity of 0.4167 meters per second with a direction opposite to the arrow, thus the negative sign. This means that the archer will briefly move backwards. Also, since the archer is relatively massive compared to the arrow, the magnitude of its velocity or the speed is comparably lesser compared to the speed of the arrow. This idea will actually validate the concept of recoil. When a cannon blasts in war movies, it will briefly move backward after firing a cannonball. We now have example number 4. Octopuses and squids thrust themselves by expelling water. They do this by storing water inside the cavity and suddenly contracting the cavity to force out the water through an opening. A squid with mass 5 kilograms, including the water inside its cavity, is initially at rest and suddenly sees a predator. A. If the squid stored 1.75 kilograms of water, at what speed should it release the water to suddenly achieve a speed of 2.50 meters per second to escape the predator? And B. How much kinetic energy does the squid create by this maneuver? In any problem, it is better for us to illustrate. On the left side, we have the initial state of our squid, and then on the right side, after expelling the water. We neglect the drag by the water so that there will be no external force on the squid water system, which makes the momentum of the system conserved. Since the squid is initially at rest, with the water inside its cavity, the initial momentum of the system is 0. We let the subscript A for the squid and B for the expelled water. Also, we let the positive x direction be the direction of the expelled water, meaning the final velocity of our squid is negative 2.50 meters per second. Solving for the release speed of the water, the mass of the release speed of the water is 1.75 kilograms. We must solve first for the mass of the squid without the water, so we have to get MA. So that is just 5 kilograms minus 1.75 kilograms. So the mass of the squid is 3.250 kilograms. Since the direction of the released water is in the positive x direction, the final velocity of the squid is negative 2.50 meters per second. We now solve for VBF. So we get positive 4.643 meters per second. The squid should release the water from its cavity at a speed of 4.643 meters per second for it to escape its predator at a speed of 2.50 meters per second. We now solve for letter B, solving for the kinetic energy created by the squid for this maneuver. We know that the initial kinetic energy is just equal to 0. We must solve for the total final kinetic energy created by the squid, and that is equal to the final kinetic energy of the expelled water and of the squid. So Kf, or the kinetic final, that is just equal to Kaf plus Kbf. Directly substituting our values, we now have the final kinetic energy, and that is 29.02 joules. Since the initial kinetic energy is 0, the kinetic energy produced by the squid is 29.02 joules. The kinetic energy is created by the work done by the squid as it expels the water.